Okay, so in probability, we've already kind of talked about kind of outcomes and how you can figure out how many outcomes. We're going to go into that a little bit more detail today. But tree diagrams. Tree diagrams are, think about if somebody makes a video game or a movie, right? Every situation, every decision is going to branch off into more decisions and more decisions and more decisions, right? The probability of something happening either increases or decreases with every single choice, okay? So a tree diagram is really an algorithm, and what it does is it tells us what we call sample space or specific outcomes. So let's say you go to Sonic, right? I want to say that they say there's like, I don't even know what they say. It's like over 1 million choices, okay? Meaning with all the different flavors and different drinks and different sizes and everything that they have, you could create 1 million different specific outcomes. Now, it would be easy to find out, just go in, multiply all the different things, and we could figure out what number it is, how many outcomes there are. But to find specific outcomes, you have to use the tree diagram, okay? And that's why the tree diagram is important. It tells you every single choice. So, and obviously, we're not going to be dealing with crazy algorithms. If you ever go into if you ever start creating games or anything like that, or do storyboards, maybe you'll do tree diagrams. But other than that, we're going to keep small tree diagrams. So, an example of this. If you spin the spinner twice, well, chances of you getting any of these is 1/3, right? So in theory, you could go, okay, yeah, it's a 1/3 chance you're going to get something, right? You spin it again, you multiply 1/3 times 1/3. So if you wanted, let's say, an A twice, you have a 1/9 chance, right? And remember, this bottom number is the outcomes. How many total outcomes? Well, there's 9 total outcomes, right? Well, in a tree diagram, you can see every single one of these 9 outcomes. So if you spin, and we call this event 1, so event 1, you have a choice between A, B, and C. Now, assuming that you get A, okay, you have event 2. In event 2, okay, you have a chance of getting A, B, or C again, right? Same if you got B, you still have a chance of getting A, B, or C again. And if you got C, you still have a chance of getting A, B, or C again, okay? So that's your tree diagram. And what you can do is you can look at it and go, okay, here are my choices. I have AA, AB, AC, BA, BB, BC, CA, CB, CC. So there's your 1, 2, 3, 4, 5, 6, 7, 8, 9 total outcomes, okay? And our specific outcomes, right, are sample space. I would read, like I said, AA, AB, AC, and then I have AB, BA. Oops, now we're on the B's. So I have BA, BB, BC, and then I have CA, CB, CC. And there's 9 outcomes, right? And it makes it easy to know every specific outcome if I want to, right? So probability of getting B twice. Well, obviously that's only going to be 1, B, B, right? So your chances of that is 1 out of 9. Okay, at least one A. Well, if you look, every single one of these choices has an A. So that would be not, oh no, sorry, they don't all have A. Come back here, look at how I guess we got BB, right? BB, and we have CC that does not include A's. So 7, right? 7 out of 9. And then no C, well, if you come over here, the ones that have no C, well, all of these have C right here. And then no C would be BB, BA, and AB, AA. So 4 out of 9. So you can see it makes it a little bit easier just to go find the probability of all these different events. So while tree diagrams are not easy to make, especially the larger ones you make, they can be useful in some situations. All right. So let's take a look at another one here. The popcorn stand offers butter or unbuttered popcorn in 3 sizes: small, medium, large. So the way I look at this is the first event is we're picking buttered or unbuttered. So buttered, unbuttered. All right. Now, you have a choice of, after, if you get butter, you have a chance. Your second event, our second choice, is small, medium, or large. Same thing for unbuttered. You have a choice of small, medium, or large. Now, you can see here, in the end, I should have 6 total outcomes, right? And you can figure that out very easily by simply going, hey, I had a 1/2 chance of butter or unbuttered times 3 chances. I got 1 and 3 for size, 1 out of 6, 6 total outcomes, right? And once again, our sample space is going to be BS. That's not funny. BM, BL, okay? And then we also have US, UM, and UL. There's your 6 different choices. And like I said, it makes it easy to go, okay, how many were buttered? Well, there's 3 buttered. Okay, so 3 out of 6, or 1/2. How many were large? Well, there are 2 out of 6, or 1/3 are going to be larges. And then small with no butter. Well, small unbuttered, there's just 1. So 1 out of 6. So that's how you make your tree diagrams. Each event, and at the very end, what's left, you can kind of just work your way up, right? Like, this is small and buttered. This is medium buttered, large buttered, okay? Now, counting principle. Counting principle, okay, is kind of what we just did. It's just an easy way to find out how many total outcomes, right? We're not actually making a fraction. We're just trying to figure out how many total outcomes there can be, okay? Basically, what we are going to do is we are multiplying, right? That's the key here. You are multiplying, okay? Multiply to find out outcomes. So, to leave her office, Karen can choose between 3 sets of stairs. Okay, so we have 3 sets of stairs and 7 doors. Each one is an event. She can pick between 3 sets of stairs. That's one choice. Okay, she can pick between 7 different doors. That's another choice. So event 1 times event 2, she has 21 total outcomes. Okay. A sweater comes in 4 sizes and 8 colors. Okay, so you have 4 sizes. That's selection 1 or event 1, and 8 colors. That's selection number 2. Okay, so 4 times 8, 32. So there are a total of 32 outcomes. There are 11 boys and 16 girls. How many can the teacher choose, or how many ways can the teacher choose 1 boy and 1 girl? Once again, you're multiplying these 2 to figure out the outcome. Okay. Here you got one. So this one, you have a dinner menu consists of 5 appetizers. So there's event 1. You can choose 5 appetizers. 12 entrees. So now you're going to have to multiply that by 12. And then 3 desserts. So we have 3 different events. 5 times 12 is 60. 60 times 3, 180 different choices. Okay. So a card is chosen from a standard deck. That's 52 outcomes times a dice is rolled. Well, there's 6 total outcomes. You're just multiplying those 2. Okay. So you can see pretty easy, relatively pretty easy to figure out how many outcomes. You're multiplying each event. Okay. I do want to do one more larger one. Like, here we go. Okay. Actually, let's do this one. So a day of the week is chosen at random, and then a coin is tossed. Well, remember, we have, actually, let's do one that has more than that. Actually, let's change this one up a bit. So a standard dice is rolled, and then the spinner is spun below, okay? Let's say before this, I also flip a coin. So if I flip a coin, that's event 1, okay? I have heads or I have tails, okay? Those are my 2 outcomes. Now, after that, I then roll the dice. Well, if I roll a dice, I have 1, 2, 3, 4, 5, 6 different outcomes, right? And if I get a tail, I still have 1, 2, 3, 4, 5, 6 outcomes, right? That would be called event 2, right? The second choice. Then finally, you're going to spin the spinner. I have a choice between red, blue, and yellow. So all of these have a choice between red, blue, and yellow. That could be red, that could be blue, and that could be yellow. And then I'm going to do the same thing for here. Red, blue, yellow. And you can see how just with this, just with 3 small choices, it's starting to get really large. In fact, I can barely do this. Like, I'm not going to be able to put red, blue, yellow without it just kind of looking really sloppy, and it just gets really messy, right? And it's a lot of work when I could easily just figure out, okay, your chances of getting tails, you have 2 outcomes, heads or tails. A dice is 6 outcomes, right? And then a spinner below is 3, and I could easily figure out 2 times 6 is 12. 12 times 3 is 36. 36 total outcomes. Remember, the tree diagram is only to tell you every specific one, such as heads, a 2, and blue. That is a specific outcome, okay, which would be part of the sample space, okay? So that's tree diagrams and outcomes. I do want you to come back over here, though, and I do want you to do 3, 4, and 6, and 7.